Hey guys, so a proof for you about the arc length of a curve. I was originally just going to go through it all, but I'll show you where I got the notes from, and then I think a better way will actually be possibly to decipher this together. So, how do I want to do this? Can I capture the entire thing? I'm going to stop right there, and then we can do the second page. The reason I'm going to do this, not because I'm lazy, I actually don't mind writing it. It's because I want you to see what an actual textbook would look like on this. So, spoiler alert, not really a spoiler alert, but I do a lot of the deciphering of mathematical language for you guys. You're not really required to sit there and read a textbook that looks like this. I mean, look at this. If you just look at this stuff, it's very complicated looking. All this stuff is super confusing, and I spent years learning how to try to decipher a lot of this. So I'm going to show you kind of how to decipher some of this and go through it with you. Okay? So it says in the section arc length. Derive one of them. Cool. We want to determine the length of the continuous function y equals f of x, just saying we have some function of x, on this interval, a to b, closed interval a to b. The derivative is continuous. That just means it's continuous and differentiable. So when they say derivative is continuous, that means the original function is continuous and differentiable. Initially, we need to estimate the length of the curve. So this is the idea behind it. This is the logic. If you have some curve and they've sectioned it off into these kind of line segments. So you see how they've sectioned it off and kind of created a bunch of linear lines. The theory is, at worst, you could do one line connecting the endpoints, and I could just find the length of this line. Technically, if you know this point and this point, you can use the distance formula and just find that distance. But that's obviously a terrible approximation. So you could do better by doing maybe, I don't know, breaking it up here and then here. Maybe that would be a better approximation. And then maybe you could do an even better approximation by breaking it up maybe even at the critical points. So here's one, find this line segment, and then find this line segment. So that's what they're doing. They're just saying, hey, rather than look at it as a smooth curve, can we just break it into a bunch of small line segments? Okay, let's erase that. Cool. All right, so that's what we're doing. And they've notated each of these points with a subscript, so P0, P1, all the way on. All right. Bam. Okay, so denote the length of each of these line segments by Pi minus 1 Pi. So for example, this line segment is P0, P1. This line segment is P1, P2. So they're creating a new notation by just slamming the 2 points together. It doesn't necessarily mean multiply the points. It just means the distance is this point and this point. They're being lazy about how to identify that. So then they're saying that the curve will approximately be however many subdivisions you do. So in this case, they're dividing it into 9. It would be from 1 to 9, and then plug in 1, so P0 to P1, plus this length from P1 to P2, plus this length from P2 to P3, plus this length from P3 to P4, and on and on and on. And then obviously we can get the exact length by taking n to be larger and larger. Obviously, you've kind of seen this before, by making n go to infinity. So if we did infinitely many, infinitely small little line segments, that would perfectly encapsulate the curve. Okay, now let's get a better grasp on the length of each of these line segments. So now they're actually going to show you how to find the length of one of these line segments. They're going to call delta y sub I as the change in y's. So they're just saying, like we've done a lot, if I do the y coordinate minus the y coordinate, I'm calling that delta y. So I have, to get those y's, I would plug in x sub I and x sub I minus 1. Basically, I would plug in the two x coordinates. So if I wanted to get this y coordinate, I would plug in its x coordinate. If I wanted to get this y coordinate, I would plug in its x coordinate. That's really what they're saying in this. We can then compute directly the length of the line segments as follows. To get this distance, for example, P0, P1, do the square root of, and it's literally the distance formula. So right here, what I'm asking in the discussion They're just using the distance formula between two unknown points, 0.0 and 0.1. And they're keeping everything general. And they're calling that distance delta x squared and then delta y, change in y squared. Yeah. So that's how they're making this jump. Now, here's where they do a little bit of work, and then I'll get rid of the screenshot and we'll scroll down. They're saying by the mean value theorem, we know this thing has to be true. Well, what are they saying here? They kind of skip a step, and I asked you about this in the discussion. Really, they're saying this, f of x sub I minus f of x sub I minus 1 all over x minus x sub I minus 1 equals the derivative. Why are they allowed to come, and that's x sub I. Why are they coming up, where did this come from? This is the mean value theorem. So when they say by the mean value theorem, what is this saying? It's saying the average rate of change of from x sub 1 to x sub 2 or something, the average rate of change has to equal the derivative somewhere. And then they're just multiplying this to the other side. So that's how they're getting this identity that they're going to use. And then notice, we've already defined what this is up here. We said that this is the same as delta y sub I. One more thing, why are they using this little asterisk here? Like, well, where did they feel like they just threw this in here? Well, they're saying that this point is not the same as this point. So they're saying for some endpoints, like this point and this point, there's a different point in the middle where the slope has to equal that average rate of change. Yeah, so that's why that asterisk is coming in. All right, so then by the mean value theorem, we know that delta y equals this thing. So now they came up with this new relationship right here. The derivative at some point in the interval times the rate of change of x, or not the rate of change, sorry, the change, the endpoint, subtracting the x coordinate endpoints, equals subtracting the y coordinate endpoints, what they've defined as delta y. All right, so scroll down. So that's where we just got using our mean value theorem. I think that's good enough. Okay, so then what are they doing? So now we can rewrite the length as this. So we started here. We had this relationship here, but now instead of this, they made this substitution. They called it delta x, which we already classified it above. And instead of yi minus y sub I minus 1, we found that that was the same as this. So that's how they replaced it with this relationship. And then notice they factored a delta x out. Where's my pen? They factored delta x out of the thing and then took the square root of it. So imagine factoring delta x squared out of both of these terms and then putting it out front. So now the exact length is given by, they're just restating. So this is a restatement of all the work. Restate. And now, this is the third thing I asked you in the discussion. They jump from this to this because this is that 3-part area series I did on how an infinite sum really is an integral. The infinite sum can be represented if I have delta x and this component in front. Those 3 pieces together allow me to say, oh, that's just literally the definition of what an integral is. And that gives us our arc length formula. And then they generalized. So they're just getting rid of the asterisk and the I, saying it's just applicable for all derivative functions. And that's it. And then that's the formula for arc length. Yeah. So this is at Paul's online notes. I use his stuff sometimes when I'm going through groups of things. But basically, it boils down to this. You're sectioning it off into smaller and smaller line segments. Each of these line segments can just be found as the distance formula. And then using this notation, they basically just say the change in y can be written as, using the mean value theorem, as really the derivative times the rate of change of x. And then they use the definition of what an infinite sum is to get that into an integral. So do you have to know all this? Of course not. I just think it's interesting. If this was a college level course, you would be doing more of this stuff. This is kind of a hybrid AP college level course. You need to know how to use it. So that's why the lesson today was super short, because really at the end of the day, it's not hard to use. Derivative goes here. It's 1 plus the derivative squared, and then just your bounds from where you're starting to where you're stopping for your a bound to your b bound. That's it. If we were doing y's, it'd be from your y bound to your other y, but we're not going to do y's. So. All right.